Let's now learn how to sketch the graph of the rational function f of x is equal to x squared divided by 1 minus 2x. Students always find this example challenging because it has a slant asymptote in it, but I'll walk you through exactly how to graph it. Just to make things easier, I went ahead and calculated f prime and f double prime, so we can just focus on the graphing and not have to worry about the derivatives. We're going to start by looking at the domain. Whenever you look at the domain of a function, you always need to be concerned where the denominator is equal to 0. So let's take the denominator of our function, 1 minus 2x, and we're going to set it equal to 0, and that gives us that x is equal to 1/2. This actually means that we are going to have a vertical asymptote at x is equal to 1/2 because our function is not defined at that point. Our domain then is going to be all points from minus infinity to 1/2 union 1/2 to infinity. So we're just going to bypass x is equal to 1/2 because that's where we have our vertical asymptote. Let's now look at intercepts. I think it's easiest if we start with the y-intercept. So to find the y-intercept, all you do is you let x be equal to 0. And if you look up at our function right up here, you can see that when x is 0, f is also 0. So we can say f of 0 is equal to 0. So our intercept is 0, 0. And this is both the x and y-intercept. Now let's think about symmetry. To find if our function is symmetric, we need to calculate f at minus x and see what that gives us. Wherever we have an x, we're going to put in minus x. So we have a minus x squared, all divided by 1 minus 2 times minus x. This is x squared, all divided by 1 plus 2x. When we compare this function to our function up above, we can see that they are not the same and they're not negatives of each other. So we can say that this is not equal to f of x or minus f of x. So that means our function does not have any symmetry. So let's just write down none. Now let's think about asymptotes and end behavior. We already found that we have one asymptote. We have a vertical asymptote. X is equal to 1/2. Now we have to think about other asymptotes. Let me go ahead and rewrite our function so we can have it in front of us. It is x squared, all divided by 1 minus 2x. Whenever you think about a horizontal asymptote or a slant asymptote, you need to look at the leading term in the numerator and the denominator. Notice that the numerator is 1 degree higher than the denominator. That tells us that we are going to have a slant asymptote. To find what our slant asymptote is, we have to do long division. I have a video on this if you need to review that. Hang with me, it won't be that bad. We are going to have x squared and we're going to divide it by 1 minus 2x. So up here under this bracket, we're going to put x squared, and then I'm going to change the order and I'm going to say minus 2x plus 1 as the part that we're dividing. It just makes it easier. Now we have to think x squared divided by minus 2x is equal to minus 1/2 x. So that's what we put up here, minus 1/2 x. And then we go ahead and multiply both terms. Minus 1/2 x times minus 2x is equal to x squared. And then 1 times minus 1/2 x is minus 1/2 x. Then we subtract, so we get a 1/2 x left. And then we have 1/2 x divided by minus 2x, that is minus 1/4. So we put that up top. And there's our answer. That wasn't too bad. So we can write down that our slant asymptote is y is equal to minus 1/2 x minus 1/4. Now we also have to think about end behavior. To find the end behavior, let me write this down. We only need to look at the leading term in the top and the bottom. So we can say f is approximately x squared over minus 2x, and this is minus 1/2 x. As x goes to minus infinity, we're going to have minus 1/2 times minus infinity, so that's infinity. And then as x goes to infinity, f is going to go to minus infinity. So our graph is going to be going up as we go to the left, and as we go to the right, our graph is going to be going down. Let's now look at increasing or decreasing intervals. For this, we need our first derivative, so let's write down f prime of x is equal to 2x minus 2x squared, and then our denominator is 1 minus 2x quantity squared. We are going to set this equal to 0. So we have 2x minus 2x squared is equal to 0. We can factor out a 2x, and that gives us 1 minus x is equal to 0. So this tells us that x is equal to 0 and x is equal to 1. We can then go ahead and draw a number line and put these points on it. We have 0 and 1, and we are going to be looking at f prime. We just need to know if f prime is positive or negative. Notice that the denominator of f prime is positive, so we don't really have to worry about that. We just have to look at the numerator. The other thing that we need to add to our number line is where our function f prime is undefined. We found that the denominator is going to be equal to 0 at 1/2. So let's put a little dotted line here, because what happens is sometimes our function can change from increasing to decreasing at a vertical asymptote. So we have to put that in our graph. Now let's pick a point to the left of 0 and see what our yellow function is equal to. So that is 2 times minus 1 minus 2 times minus 1 squared. So this is minus 2 minus 2. That is negative. So we'll put a negative right here. Now we have to pick a point between 0 and 1/2. So let's pick 1/4. So 2 times 1/4 minus 2 times 1/4 squared. That is going to be positive. So we'll put a positive here. And now let's pick a point to the right of 1/2. So let's pick maybe 3/4. That is also greater than 0. So we're going to put a plus here. And then if we look in this region to the right of 1, the only thing we have to really look at is this term right here. That's the biggest term. It is negative. So we know that f prime is going to be negative. That was pretty complicated, but we did it. Let's go ahead and put increasing and decreasing lines. Our function is decreasing here, increasing on each side of our vertical asymptote, and then decreasing here. Let's go ahead and write that down. It is increasing from 0 to 1/2 and from 1/2 to 1. Notice we cannot say that it's increasing at 1/2 because we have a vertical asymptote there. And then it is decreasing from minus infinity to 0 and from 1 to infinity. Let's now look at local max and mins. If we go back up to our graph, we can see that we are going to have a local min at 0 and a local max at 1. Let's write that down. We have a local min at x is equal to 0, and we have a local max at x is equal to 1. Now what we have to do is find the value of the function at both of those points. So let me put that our function f is x squared all divided by 1 minus 2x. So f at 0, let's see, that is 0 over 1, so that's just 0. And then f at 1 is 1 over 1 minus 2, so that is minus 1. We can then say that our local min is 0, 0, and our local max is equal to 1 minus 1. We have one more thing to calculate, and that is concavity and inflection points. To find concavity, we always need to look at the second derivative, so I'm going to write that down. F double prime of x was 2 all divided by 1 minus 2x cubed. We can see that f double prime is never going to be equal to 0. But let's go ahead and let's look at our function again. Our original function is x squared divided by 1 minus 2x. Concavity can change where our function is undefined, and that is going to be at 1/2. Let's go ahead and let's draw a number line, and let's put the point 1/2, and then we'll have a little dotted line here because we have a vertical asymptote there. Now what we're going to do is we're going to look at f double prime to the left and right of this point. Here, we could pick a point x is equal to 0, and let's look at the value of f double prime. It is going to be positive. And then to the right here, we could let x be equal to 1, and f double prime is going to be negative. So this tells us that our graph is concave up to the left of our vertical asymptote and concave down to the right. We have concave up from minus infinity to 1/2, and then we have concave down from 1/2 to infinity. Because we do not have a point where the concavity changes, it only changes at an asymptote, we have no inflection point. Let's write down no IP. Now let's go ahead and put everything that we just calculated on our graph. I think the best thing to do is to put our asymptotes and our points on our graph first. We found that we have a vertical asymptote at 1/2. So I'm going to go ahead and put this on our graph. And let's go down here and see what else we have. We have a slant asymptote, and I'm going to put our slant asymptote up here. We found that our slant asymptote was y is equal to minus 1/2 x minus 1/4. Let's go ahead and let's graph this. Let's see, when x is 0, y is minus 1/4. So we have this point right here. And then when x is minus 1, we have y is equal to 1/2 minus 1/4, which is 1/4. And that point is right here. Now we can go ahead and draw our asymptote. Try to be as neat as we can. Now let's see what else we can put on here. Going down, we have a local min at 0, 0 and a local max at 1 minus 1. So here is our min, and then our max is going to be right here. And let's see, increasing, decreasing. It's increasing on either side of our asymptote and then decreasing on the right and left of our max and mins. And it is going over here, concave up to the left of our asymptote. Now I think we can go ahead and draw our function. It's going to hug the asymptote, and it's going to come down here, and it's going to curve up. And then it's going to be concave down, so it's going to follow this asymptote, reach our max, and then follow this asymptote. And that's it.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.